It is possibly the most revolutionary invention of the last 50 years. Since they were invented, microchips have evolved and have become electronic superbrains, capable of performing over 1 billion calculations per second. Creating these extraordinary miniature electronic brains is one of the most complex tasks ever done. But how are silicon microprocessors made? Discover the amazing process of producing billions of microchips in a semiconductor factory. Modern microprocessors contain billions of transistors on a single chip, and most electronic devices today use them. In 1958, the inventor of integrated circuits, Jack Kilby, managed to put a single transistor in his design. The latest generation uses nearly 1 billion transistors, and according to Moore's law, this number doubles every 2 years. This company produces 70 billion microchips a year, which are used in many devices from washing machines to smart cars, and each one of them is a miracle of miniature manufacturing. A processor works thanks to the circuits of millions of individual components called transistors. The more transistors we put on a chip, the faster and more powerful it will be. In this amazing and futuristic-looking factory, silicon sheets are produced, which are the foundation of all modern microchips. The substrates for microchips are made from quartz sand and are called silicon wafers. Silicon possesses distinctive characteristics due to its classification as a semiconductor. This means that depending on how it's treated, silicon can either conduct or block electric currents. It is this property that makes it perfect as a support for the millions of tiny transistors needed to make a modern microprocessor. The problem is that, since these transistors are so small, the silicon base on which they rest has to be completely perfect. It took decades to perfect the manufacturing process of silicon with a perfect monocrystalline structure. To manufacture these wafers, a huge single crystal is extracted from the melted mass of purified silicon. It starts with polycrystalline silicon, which is heated to about 1420 degrees Celsius inside a special sealed oven. This oven has been purged with argon gas to eliminate air. The melted silicon we get is spun in a crucible. The result is a silicon crystal that weighs about 200 kilograms and has a diameter of about 200 millimeters. The crystal is so strong that it supports its entire weight with a single thread that is 3 millimeters thick. So after several tests with chemicals and X-rays, it is put into a silicon wafer cutter. This 10-ton cable saw uses a network of very thin cables that move very quickly to produce silicon wafers. They are only 2/3 of a millimeter thick with a purity of 99.9%. But once cut, microscopic marks have been left on the surface, so they must be polished through a process called lapping. But even after going through this modern polisher, the sheets are not smooth enough, so they have to be polished again through a chemical process. The result is silicon wafers with a surface roughness of less than 0.1 nanometers. Already completely polished, they are now finally ready to start with the circuit design. Using computer-aided design software, engineers create the detailed design of the circuit. Once the circuit design is completed, a thorough verification is carried out to ensure it meets the required specifications. 25 wafers are packed in a completely sealed container and sent on a journey that will take them through hundreds of manufacturing steps. Placing millions of transistors on these small sheets is the job of chip manufacturers. The problem for this factory is that these transistors are about 200 times smaller than a red blood cell, and making something so small is a huge production challenge. Fortunately, there's a machine that does it. It's a photolithography machine, and it can print billions of transistors on silicon wafers every hour. Before entering the machine, each plate is covered with a liquid that reacts to light. This is what is called the photoresist, and it reacts to light like the film of a camera in a dark room. The photoresist is a chemical agent, very sensitive to light. That's why this room has a yellow light. Otherwise, normal daylight would spoil the plate. Photolithography techniques project circuit structures onto semiconductor wafers, similar to the way images are transferred in slide projection. The machine emits a laser that crosses the designed plane of a transistor and engraves it on the silicon plates. Just like in a photo, this leaves an image of the transistor on the plate. When the chemical is removed, the design remains like a photographic image. However, to place all components on the sheet, it must be done layer by layer. To complete the process, the sheets undergo the same cycle multiple times, typically repeating between 15 and 40 cycles. Transistors are built level by level, like mini skyscrapers, which results in hundreds of microchips, each of which has more than 1 billion transistors. The challenge is to double the number of transistors on a chip every 2 years to meet the demand for increasingly powerful devices and computers. The biggest challenge for engineers is finding new ways to improve the laser beam that engraves the shape of each transistor. They discovered that by passing the laser beam through a layer of water, similar to sunlight passing through a magnifying glass, they can significantly increase the beam's intensity. This innovative approach allows for the reduction of transistor dimensions to about 5 times smaller than the smallest bacteria. However, building machines that rely on this level of precision is a nightmare. It takes 3 months to assemble and test the 800 circuits, 1,300 cables, and 400 boards that make up these water-enhanced machines for making transistors. The finished product will help produce smaller and more powerful microchips. Working at this microscopic scale poses a significant challenge for microchip manufacturers. When a transistor has a width of only 1,000th of a millimeter, the smallest particle of dust can cause a short circuit. A single particle landing in an area can destroy a chip. So before workers get to work in the factory, they must put on the protective suit. The manufacturing process takes place in a clean room of almost 18,000 square meters. Thanks to 12,000 tons of air conditioning equipment, the air in this room is a lot cleaner than that in an operating room. Every employee must take an air shower every time they enter a clean room to remove invisible particles of dirt and dust. The entire air inside the factory is refreshed every 2 minutes, making it 10,000 times cleaner than outside air. Copper dominates the next step of the process. The thinnest interconnecting wires join billions of separate transistors to form the integrated circuits. Before that happens, cleaning is essential for wafers, as particles lurk at every stage of the manufacturing process. Before pouring copper into the trenches for interconnections, a barrier layer is applied to help prevent short circuits and ensure reliability. Then the trenches are filled with copper. The leftover copper is ground down to the edges of the trenches, isolating each interconnection from the others. In 2 months, the wafer is ready. While individual conductors within the integrated circuits are typically measured in micrometers or millimeters, the cumulative length of all conductive traces can extend over several kilometers. These intricate circuits connect 100 billion transistors on numerous levels, all within a space no larger than a fingernail. The finished silicon sheets carry up to 1,000 different microchips and over 4 trillion circuit components. Now, they just need to be cut and trimmed, and the long journey from being sand to a circuit board will be complete. The final step in microprocessor production is chip encapsulation. To prepare for this step, tin and silver granules are applied to the wafer. These will bond the chip to the frame. What was once a pile of worthless sand can now be sold for hundreds of dollars per gram, showcasing the remarkable transformation in semiconductor manufacturing. If you want to know how AI robots are made, watch the video on your screen. And please like the video if you enjoyed it and share it with someone who might be interested. Also, subscribe to this channel by activating the notifications to continue learning. Thanks for watching.